prior to lunch, we still have two relatively short presentations. And the first one is going to be on how to capture EEG data if you don't record it yourself. And the second one is going to be on how to analyze it, so which tools we use for analyzing EEG data. What we've been focusing on the last few days is very much to record your own data and to run your own experiment. But there can be situations where you're not going to work analyzing your own data because you might not have your own EEG equipment. But it might also be because you're working together with other people over multiple labs. For example, collecting data from a patient population where you have a few patients, someone else has a few patients, etc. To combine data with multiple labs is an important application where you would be analyzing data that comes from others. And simply, you want to use others' data. So what I'm going to cover is where to find data, how data is formatted. I'm going to cover the brain EEG data structure, which is an important initiative, international project in standardizing data representation. I'm going to highlight what the important things are that you need to know from data that you're downloading from someone else. So the focus is now not so much going to be on this side, but there is still an important aspect in analyzing the data, but also knowing about what the task is in which the data was acquired. So, ideally I would say, if you do research using EEG in your own lab, you're defining your own research question, you make the task, you make the similar material, you select the participants, that's also an important one, we're not really discussing it here. You do the experiment to record data as we were doing yesterday, and you can analyze it yourself. And after lunch, we're going to move on to the analysis. However, as we've discussed on the first day, setting up and maintaining an EEG lab is expensive. And a lot of you don't have an EEG lab at this moment. But also getting participants, including recorders, it's a lot of work, as you see. It's not only recording, it's also the preparation, it's designing the experiment, which is a lot of work. It's also cleaning up, maintaining the lab, which is a lot of work. So that means that you can also reuse data that was recorded for others. And especially for teaching, that's something that we do most. So a lot of our PhD students, they start their PhD projects by analyzing data that was recorded by people that were in the lab before them. So we often have data sets being used multiple times. Sometimes you want to collaborate. So you contribute to the research question, to the task, and the stimulus material. You find your local participants, you find the record data from your local participants, and then your collaborators elsewhere, they also find participants, and they also record from them, and then you put the data together. Then you can analyze it yourself, you can analyze it together. This is not trivial, because first you have to agree upon the research question, the task, and the stimulus material, and then you have to make sure that it works with all the different labs that are collaborating. Also, the recording, labs might have different equipment. So that means that part of the experiment might have to be adjusted to accommodate the different trigger setups, the different audio, video devices, etc. So this is also quite challenging. So it is important, if you want to analyze the data that you've collected over multiple labs, the data should be sufficiently comparable to all labs. It doesn't have to be identical, but it should be sufficiently comparable. And also important is that you need to have data transfer agreements between the different labs such that you're legally allowed to work with data from another lab or vice versa. So this is something that you have to think of in advance if you start working together. Tomorrow morning I'm going to have a lecture on research ethics and legal constraints, and tomorrow afternoon David is going to give a lecture on ethics and legal constraints specifically for Africa. We're going to cover this in more detail. Sometimes you just want to analyze. If you want to analyze, you have a limited extent to which you can define the research question. So you can search for data sets that have a similar research question as the one that you have in mind, but you cannot really control it. You're not making the task, you're not selecting the participants, you're not doing the recordings, but you can analyze. So some things limit you in the flexibility that you have, whereas other things are actually way easier. Not having to bother about the first four topics means that you can go to the analysis really quickly, but perhaps the outputs that you have are not really in the direction that's why you need to go. So, why would you report data if you can use data reported by others? It's very useful for, like, if you use data by others, it's very useful for generic data. For example, resting state data. If you participants here or participants in their own place, if they rest, there's not really that much reason to assume that their resting state activity is going to be different. And the same goes for simple, like old-fashioned experiments. A lot of experiments have already been done by others. If you want to analyze such an experiment, you have to use data that is reported by others. It's useful for teaching and training, and it's useful for trying out an analysis prior to pre-registration. Pre-registration, what we're going to see is that in the analysis, there's a lot of choices that you have to make. And that gives a lot of analytical freedom. And that is, in a way, risky for your statistical analysis, because there's many paths that you can take during your analysis. And with pre-registration, that is a strategy that we have agreed upon as research scientists, so that we agree upon fault and that we register what we're going to do in terms of analysis. Because if you've never done an analysis before, it's very difficult to write out what you're going to do in analysis. So data that is provided by others allows you to try out an analysis and to settle on the analysis strategy prior to applying the analysis strategy in your data. So this will become more and more important in the future as well. A very important aspect of using data that is provided to others is open science. Open science is much more than just data. Open science also involves open access publications. So that you can read papers without you having to pay for it. Open data is one of them, open source is one of them. Scientify is open source, Future is open source. Open materials doesn't apply so much for EEG research, although, for example, the design of the Harcourt blocks that we use for synchronization, you can see that as open materials, and pre-registration is also one of them. So open science is a very broad concept, and data is one of them. So then the question would be, where can you download data? So there's repositories, there's multiple repositories, and you can think of these repositories in different ways. We have very generic repositories, where any type of data will be stored. And an example of that is Nodo or OSEP. Some of these generic repositories are managed by publishers. DataWire is one of them, Picture is one of them. We also have institutional repositories that are general purpose. So for example, at our university, Harcourt University is managed our U.NL, that's our website. We have a data repository that is being used by all the researchers from all over the university. So in our repository you can find EEG data, which is also find chemistry data, data from humanities, data from very different fields. And there's national repositories. So in the Netherlands we have data.nl. That's a collaboration between a number of universities that do not have their own repository. And we have technical universities have their own data repository as well. So these are all generic data repositories. And the consequence is that they're not so explicit about the types of data that you can find. So you have to put a little bit more effort in finding these data sets, because you have to find them as if all the books in the library are unsorted. Because if the books are nice and sorted, it's much easier to find the book of the author that you're looking for. We also have domain-specific repositories. And for neuroscience and neuroimaging, there's a number of repositories that have a lot of data sets. I would say the biggest one is OpenNeuro. OpenNeuro.org is a repository in the US that has a lot of neuroimaging data. Most of it is MRI and fMRI, but there's also a lot of EEG data sets there. There's also MEG data sets, there's PET data sets, and some other things. In Europe, we have Public Neuro, which has relatively recently started. It does not show any data sets yet. I don't know whether there's EEG. Neuro, I think there's like at least 100 each data sets. Each of these data sets has like 20 to 50 to 100 participants. And then here we also have E-brain, which is from the European Union. And E-brain is more aimed towards clinical data. I'm not really sure how many EEG data sets are out there. If I would pick between these, I would first look at the world. Then, making it more specific, we have project-specific repositories. So we, for example, have EEG-net and VisionNet. So EEG-net is a Canadian project, which is really about recording and sharing EEG data. So they provide very detailed information about how they've designed their studies, how they've recorded their data. VisionNet is not so specific for EEG, but it's more for clinical neurophysiology, EEG being one of them, but it also has electrocardiography data, electromyography data, those types of data, often recorded in a clinical setting. That's quite a decent description of the data, but the data is much more clinically oriented, so it's not so much task oriented. And then finally, one place where you can find data is if you find a research publication, or if you find a data descriptive paper, then in the publication there's often a link nowadays to where the data is being shared. So that means that if you're reading the literature, you might find in the papers that you're reading, that you're reviewing, and that you're basing your own research on, you might find one paper that actually shares the data, and of course on the basis of that you can also find your own research. One important journal in that respect is Scientific Data. Scientific Data is a journal from Nature Springer. And Scientific Data is a journal in which we publish data sets. So it's actually not that the data set is published in a journal, because the journal is just like a published PDF. But it's the data descriptor papers, so it's papers that describe the data set in great detail that are being published in this data set, in this journal. And then the requirement for scientific data is that if you describe the data, you also have to provide a pointer to where the data is. So this is really an excellent place to find very detailed description of the data, plus the data that goes with it. Generic repositories are broad, and they don't expose a lot of metadata. So that means that you have to dig quite deep into the data set to figure out what task was used, which stimuli were used, what administrative code. Project-specific repositories are very deep. They expose a lot of metadata and search capabilities. I would say the domain-specific repositories such as OpenEuro are a little bit in between. On OpenEuro, it's very easy to find EEG data sets. But if you want to know very detailed what was done, you still have to go in and have a look at all the details. Okay, so this is really like where do you start if you look for data. Of course, you can also search for data. You can use a search engine. And we have general search engines like Google, etc. But for data sets, we have also specific search engines. So Google has a specific site, data set search, lots of research on Google.com. I'm pretty sure that in the future they're going to make this part of their regular search engine. The same way if you search for images, where you don't really have to go to special data group. And almost the data site report is also one of these places where you can specifically search for data sets. And that's of course handy because then you can use keywords. And you know that you're not first going to wait through all of the web pages before you find web pages for the data set. And so I'm sharing these slides, and I'm really asking you to try out these places, try out the search engines so that you can see what data sets you can find. Relatively recent development is to make search engines that are very specific for data. Two of these very specific search tools in the domain of neuroscience are NeuroLabel and DataLab. So NeuroLabel is a platform and a tool that is specifically designed for searching through clinical data sets. And it's designed for searching through clinical data sets that are hosted by different universities. If you find the data sets that you want, or if you find the notations that you want, your label does not directly provide you with the download. Your label provides you with information, where you can go, or the contact information of the person who you can contact to download the data. Because this is very useful, because this allows you to, for example, search very specifically on patients with a specific age, with a specific gender, with a specific clinical diagnosis, etc. Which are things that you cannot do with more generic subject. Okay, so imagine that you found a data set that you find interesting and you download it. Then there's a number of things that you have to look out for. What you've seen in the last 3 days is that there's a lot of details in the recording and in the experimental task. So you have to know what is the task or the experiment during which the EEG was recorded. What are the trigger codes that we use? This morning when we showed the triggering, we used trigger code 1 for the standards and trigger code 2 for the ABDN. Well, in such a task it's quite simple to determine this. You just look at the triggers. If you see a lot of 1s and occasionally 2, well then you know that the 1 is the standard, 2 is the ABDN. But of course, if you download the data set and there's a bunch of trigger codes, we don't know how these numbers, how they map these experimental conditions. So that is always an important thing that you should look for, is whether the data sets provide enough detail so that you can de-itemize it. This afternoon, in the hands-on session, we're going to look at a data set that has a relatively complex experimental design. I think it has something like 16 different conditions, which also means that there are 16 different trigger codes. So knowing which trigger code goes with which condition, of course, is then very important. So you need some sort of table, you need documentation. Also important is what the file format in which the data is shared. And not all file formats can be read in all softwares. An important concept that a lot of institutes are now following is the concept of fair data. Fair data means that data is findable, accessible, interoperable, and reusable. Findable means that you can search, that if someone searches for it, that they can find it. Accessible means that you know under which conditions the data can be accessed. Interoperable means that the data can be read by someone else who wants to use the data. And reusable means that the data has enough documentation so that not only can you read it in the computer, but that you also understand it. So for example, the table is really good. So the fair writing principles is a very important strategy that we're now using when we share our data sets. So I would say the same way as we're using open access to publish our papers, using fair principles for publishing our data. In order to make EEG data fair, an important project that started about 10 years ago is this, Brain Imaging Data Structure. And that is a community initiative to make data more fair and to improve data sharing. And especially improve interoperability and reusability. So this is a project that uses existing file formats, but that puts these file formats in a structure where there's also space for metadata. So if you look here, what you can see is that there is a directory structure. So the files are organized according to a well-specified directory structure. And here is actually the EEG file. If we were to share this data conventionally, we would only get the file. There's so much information missing from the file. And for that we have a lot of metadata. So for example, there's metadata on the general description of the data set, what's the purpose of the data set, who are the authors. There's information about the participants, what is their age, what is their gender, those type of things. But there's also information about the task, about the EEG system, about electrode measurements, about the recording system of which enters, very important about the events, so that you don't have to think, that you don't have to guess what the numbers mean in the data file, but you actually have textual descriptions. So all of these small files that are next to the large data file They are considered sidecar files. And they represent data that is otherwise missing from the recording. So they make it easier to query, to search. And as an example, here we just highlight some of the sidecar files. We have the participants file. That's just it's a TSV file. So TSV stands for tab separated values. It's just a table. You can read it in Excel. And it contains, for every participant, it contains a number of columns where it specifies the characteristics of those participants. We have a sessions file, if the participant comes back multiple sessions, so that you can document what the different sessions are. We have a scans file, which is a little bit based on my terminology. That's where you have multiple runs in the experiment. And then within one of the recordings, we have the EEG file, which specifies the type of equipment that was used, but also where was the reference electrode placed, what is the ground electrodes, what is the layout of the electrode cap, so what type of electrode cap did you use, what type of amplifier did you use, what type of filter settings did you use. All of these are snippets of information that are typically not available in the original EEG file. So they're only available to the person that did the recording in the lab. Then there can be a channels file, which specifies all the channels that were in the recording, including whether the channel is good or bad, or other information. An electrode file is with recording electrode positions, and a recording system file, so that we know how the spatial coordinates are used. And to just get an idea, this is an example of an EEG to JSON file. So this is a file format that you can just open in a text editor. And what you can see is that this is a recording that was done with the Brain products, Brain MPC, and also the cap was made by Brain products. And it's active cap for 64 channel standards 2. And that is a type of cap that you then can look up on the Brain products website, and you can find more details. There's 10 EEG channels that we used. The reference was unipolar, placed in FZ. Over here, the ground was placed in AZ, like material, like that. It was done probably in Europe, with 50 Hz line noise. If you were done in the US, it would be 60 Hz. Placement scheme is according to the 10% system, etc. So these are all things that help to interpret the data set. This is an example of the channels JSON file. So what you see is the different channels that we used. They're all EEG channels. The units are on microvolts. They're all good except for this one. And then here it has a description, so this has no correlation with other channels. So if the person who has acquired the data has already taken notes, then this is the page where these notes can be stored in the archive. There's no guarantee that you're going to get all of these columns. It might be that you're just going to get the data that you still have to figure out yourself, which sounds good. That's a place where you can store this information. So, if we zoom out a little bit and just think about how our EEG data set details documented, then on the one hand we have the elemental section of the paper that initially uses the data. That's where you find details about the EEG recording. That's why you find details about the participants. They don't have that much detail. There can be a data descriptive paper, as in scientific data, that will have more detail. If you then actually have the data, and hopefully there's a degree text file or a Word document or a PDF, that's going to have more detail. And the bits metadata or the sidecar files, they provide the most detail. So that's why searching for bits data sets is very good strategy, because you know that they're coming with a lot of metadata. Whereas if you search in the meta section of the paper, there might be important information missing. For example, in the paper, I never see which trigger codes we use. It just says we use this amplifier, which means if you have the data, you still don't know how to read it and how to process it. And that's also, there's no space for that in the paper. That's what is using. So what I had in mind, and if the internet allows me, is just to quickly show you how these data sets look like. So what I would like you to do is to come up, like so one of you, come up with a data set that you would like to try to find. And I'm going to try to find it.